Hello, I am Seunghun and from MLab, and I'll give a presentation about our paper, Latent Bayesian Optimization via Autoregressive Normalizing Flows. Bayesian optimization is a method to efficiently optimize a black box function fx. In our case, the goal is to find the input that maximizes this function. It's widely used in applications like automated design, drug discovery, and more. The function we are trying to optimize is often complex and expensive, and it is a black box function. We can evaluate it, but we don't know about other information like gradients. This is where Bayesian optimization comes in. It uses a probabilistic surrogate model, and this predicts the objective value with uncertainty. Then we have an acquisition function. It uses the surrogate model to decide where to evaluate next. We pick the point with the highest acquisition value, like this red point, and evaluate the objective function. Then we repeat this process, search, evaluate, update, until we find the optimum. But in many real problems, the feasible set is often complex, like structured or discrete. In that case, latent Bayesian optimization can be a solution of this. Latent Bayesian optimization performs Bayesian optimization within the latent space. For this, use a generative model like a VAE to map inputs into the latent space. The figure is the overall process of latent Bayesian optimization. First, the observed set X is encoded to the latent space with encoder Q5, and then conduct the Bayesian optimization based on the latent representations and their corresponding objective values to select the next query point. And the decoder maps the latent of the next query point back into the input space. The black box function is evaluated at the new input x tilde and update the data. But there is a problem, which called the value discrepancy problem. These molecular pairs on the left and right, they look almost the same, but their objective scores are actually very different. When we zoom in, we can see small changes, and that makes a big score gaps. Let's say if we have an input X with the high score Y, and here's the corresponding molecule. And then what if we pass it through the encoder decoder? After reconstruction, we get X hat, and score Y hat can be much lower. It looks like reconstruction worked well though. This is the value discrepancy problem. It happens because the encoder-decoder doesn't reconstruction perfectly. The figure below shows the example of the value discrepancy problem using the objective score distribution. The blue one shows the original scores, and the orange one is after reconstruction. In optimization, we focus on inputs have high score. So here, we use the data with high scores. As you can see, the objective values are decreasing after reconstruction. And this is a reconstruction example from this molecular design task. After reconstruction, the objective values is significantly decreased. And we can resolve this problem with normalizing flows. They use the flow and its inverse operation to map between spaces. Our overall NFBO process works as in the figure, which is similar to latent Bayesian optimization process, encoding BO over input space, latent space, and decoding evaluation. At first, take a closer look at this SeqFlow. We propose a flow model for discrete sequences, like text or smiles. To handle discrete data, we used autoregressive normalizing flows. Previous autoregressive normalizing flows were designed for continuous data, or they couldn't reconstruct discrete sequence perfectly. Then we propose SeqFlow, which can perfectly reconstruct the discrete sequences. The figure below shows the encoding and decoding process of SeqFlow. We start from X, which is the token sequence, and embed it, and After through the flow, we obtain the latent representation jet, and with the inverse flow, we can obtain the embedding V just as before. And then we convert the embedding V into the input X. The point is that after the entire reconstruction process, the decoded X is exactly the same as the original input. In particular, we ensured perfect reconstruction by designing the embedding to token function as the left inverse of the token to embedding function. Here we define the embedding function as H and the overall flow as G. The inverse flow is G inverse and the embedding to token function X as left inverse. That means H inverse of H of X equals X. Using the proposition, we show that the entire encoding and that is composition G and H also has a left inverse. And its left inverse is the entire decoding process. This means that X can be reconstructed exactly through this encoding and decoding. And take an example to see how the encoder and decoder works in detail, and show the process that included. At first, the discrete sequence input X, like an atom sequence such as COC, is embedded into the V through the dictionary. And we obtain the latent representation jet through the flow G, and select the next query point jet tilde, and apply the inverse flow to get the embedding. And we select the most similar embedding from the embedding set from the dictionary to transform the embedding to discrete sequence. Finally, we evaluate the function and update the data. In this overall process, if we focus the embedding function, we denote it as H just as before. Proposition 2 shows that the embedding function we designed is injective, and its left inverse is embedding to token function. And by proposition 1, this function guarantees that we can perfectly reconstruct the original sequence from the latent space. And lastly, we can change the way candidates are selected for search in the latent space. We present the token level adaptive candidate sampling, which adaptively choose the latent tokens Zi that we have to exploration more, and the selection of the token is determined based on the pointwise mutual information between each token of Z and the sequence X. Specifically, the probability of sampling and perturbing token is given by the equation below. The pointwise mutual information between the discrete sequence X and a latent token Zi is denoted as omega I, and this PMI value is used to compute the perturbation probability pi I. We conducted experiments on 2 molecular design benchmarks. The table on the left shows the results from the practical molecular optimization, and the right side is the results from the guacamole benchmarks. The number of in the table represents the sum of the scores across 23 tasks and the rank of this. As seen in both the table and the figure, our NFBO outperforms various existing methods, showing its strong optimization performance. We compare our base generative model TextFlow with our SeqFlow in 2 aspects. First, reconstruction ability, and second, optimization performance. Both models use the same normalizing flow component. We evaluate the reconstruction ability by checking how often the reconstructed value y hat is different from the original value y, which is in the table. As you can see, TextFlow fails to reconstruct accurately because it uses a bias LSTM-based mapping that isn't invertible. But our SeqFlow achieves perfect reconstruction, as in the table. SeqFlows gets no error across all tasks. And second, optimizing performance. TextFlow actually has more parameters, but it shows similar performance to the baselines because it reconstruction ability. Our SeqFlow has fewer parameters and reconstructs perfectly, and it performs much better in these molecular design tasks. It is an analysis of our tasks. The figure on the left shows the PMI values between each token I and the input sequence. As you can see, some of the tokens have relatively high PMI values, and due to the autoregressive nature, the former tokens tend to have higher PMI values. As shown in the right figure, the model with applying tax generates a higher ratio of distinct candidates, improving diversity in the search process. And as a conclusion, we propose NFBO which can perfect reconstruction and resolve the value discrepancy problem in latent Bayesian optimization. And thank you for listening.